Hello everyone, this is a video on thermodynamics. Here we are already doing. If you check my playlist, we are already doing a numerical series on quantum mechanics, then electrodynamics, hmm, statistical mechanics, and also there are so many videos on atomic and molecular physics. Okay, so these are mark fetching subjects in GATE. So there is another one which is kind of easier and also mark fetching, that is thermodynamics. Okay, so this series will be focusing on thermodynamics where we will have like 10 to 15 sessions. We'll be solving numericals. I assume that you have studied theory, okay, and based on that, we will do numericals here. Okay, this is basically a numerical session, and through this numerical session, also we'll be going through a lot of theories which will clear your doubts. But I assume that you have studied theory, okay, before that. All right. Yeah. So we'll do very like sequentially from basic to like a tough and like syllabus wise. So okay. So okay, let's write the first question. First question is calculate the average. um, Calculate the average thermal energy. The average thermal energy of a diatomic molecule. Diatomic molecule in both low temperature, and high temperature condition. Both low temperature and high temperature condition. Okay. Calculate the average thermal energy of a diatomic molecule in both low temperature and high temperature condition. Okay. So how to calculate it? See, at low temperature, what happens? At low temperature, degree of freedom in like translational degree of freedom is 3, and rotational degree of freedom is 2. Rotational degree of freedom is 2. Translational is 3, rotational is 2. So therefore, your average energy will become how much? 3 into half kBT, okay, plus 2 into half kBT. Half kBT into 1, like translation degree of freedom, half kBT into rotational degree of freedom. Alright, that will give me 3 by 2 kBT plus 2 by 2 kBT. That will be your 5 by 2 kBT. Okay, that will be 5 by 2 kBT. That is what, yeah, at low temperature. Okay, so what happens at high temperature? At high temperature, what happens? If translation degree of freedom is 3, rotational degree of freedom is 2, but there is another one, that is vibrational. Because of high temperature, the molecule will also vibrate, isn't it? So vibrational degree of freedom will also be there. That is your 1. Translation is 3, rotational is 2, vibrational is 1. So average energy will be again 3 by 2, 3 into half kBT plus 2 into half kBT plus 1 into half kBT. Alright. So that will be giving me 3 by 2 plus 2 by 2 plus 1 by 2, right? Or no, this will be vibration. For vibration, it will be only 1 into kBT. Okay, so that is 1. So 3 by 2 plus 2, that is 7 by 2 kBT. Okay, kBT. Fine. is 7 by 2. Is that all right? Hmm? If translation is 3. Yeah. So this is the first question on this. We have to calculate the average energy using our degree of freedom and all. Okay. I hope you understood this one. Next question number 2. A gas mixture consists of gas mixture consists of 2 moles of oxygen and 4 moles of argon, 4 moles of argon at a temperature T. Neglecting all neglecting all vibrational modes, neglecting all vibrational modes, the total internal energy of the system is okay. Gas mixture consists of 2 moles of oxygen and 4 moles of argon at temperature T. Neglecting all vibrational modes, the total internal energy of the system is how much? 2 moles of oxygen and 4 moles of argon at temperature T. Neglecting all vibrational modes, total energy of the system. So, we know internal energy of n moles of an ideal gas with no vibrational degree of freedom, with no vibrational degree of freedom at temperature T is internal energy of n moles of an ideal gas with no vibrational degree of freedom at temperature T is U is equal to n F by 2 RT. N F by 2 RT, right? N is your n moles of an ideal gas. This is n moles, and F is the degree of freedom. So N F by 2 RT. So F is the degree of freedom. Okay. So F is what is given? F is gas consists of 2 moles of O2 and 4 moles of argon. So we you have to remember this. F is actually 5 for O2. Okay, but it is only 3 for argon. You have to remember this. Okay, 3 for O, 5 for O2 diatomic gas. This is monatomic 3 for argon. So we will do what? We will do what? We will do U is equal to UO2 plus U argon, isn't it? We know we just wrote F for O2 is 5, F for argon is 3. So O2 5 by 2 RT. Okay, okay, wait. U is again I will write UN F by 2 RT. UO2 will be how many moles of U? 2 moles of U. 2 into F by 2 that is 5 by 2 RT. How many moles of argon? 4 moles of argon. So 4 into argon is 3 by 2 RT. Yeah. So I'll put it here. U is equal to UO2 that is 5 RT plus UAR that is 6 RT. Alright. So this will give me 11 RT. So this is 11 RT is the what? Is the total energy of the system. The internal energy. Total internal energy of the system. Alright. Next question, question number three. Okay. In one dimension, an ensemble of n classical particles has energy of the form is equal to px square by 2m plus half kx square. The average internal energy of the system at temperature T. Okay. In Monty, an ensemble of n classical particles has energy of the form E is equal to px square by 2m plus half kx square. Okay. The average internal energy of the system at temperature T is how much? Okay, so E is given as px square by 2m plus half kx square. Average internal energy. How will you calculate it? See, we'll use equipartition theorem here. So according to write down according to equipartition theorem, contribution of each quadratic term, contribution of each quadratic term in Hamiltonian to thermal energy, to average thermal energy is half kVt. So the contribution of each quadratic term is half kVt according to equipartition theorem. Okay. So here what will happen? Here see two quadratic terms, right? So what will be the answer then? You will be two to so each quadratic term. So this one will give me half kVt plus this one will give me half kVt. So both will add up to give me kBt. Okay, but there are how many particles? N classical particles. So this is for one particle. For one particle, your average energy is half plus half 1 kBt. So for n particles, it will be how much? Your average will be n kBt. Okay, that will be the answer. Is it all right? Okay, just see through it once and let me know if you have any doubts. So we'll move to the next question. The classical gas of molecules, each of mass m, is in thermal equilibrium at the at the absolute temperature T. The velocity components of the molecules along the Cartesian axis are Vx, Vy, and Vz. The mean value of Vx plus Vy whole square is, okay, option A is kBt by m, option B 3 by 2 kBt by m, half kBt by m, option D 2 kBt by m. Classical gas of molecules, each of mass m, is in thermal equilibrium at absolute temperature T. The velocity component of the molecules along the Cartesian axis are Vx, Vy, and Vz. The mean value of Vx plus Vy whole square is, okay. So the mean value of Vx plus Vy whole square is asked. So Vx plus Vy whole square mean value is equal to how much? Mean value of Vx square plus mean value of Vy square, mean value of 2 Vx square. Okay. So putting Vx square is equal to Vy square is equal to Vz square is equal to how much? This is your kBt by m. Hmm. This is actually kBt by m. Okay. So how is it kBt by m? Because if you see your half mv square is what? Half mv square is, we know 3 by 2 kBt. Your kinetic energy is 3 by 2 kBt. Your kinetic energy is what? Half mv square is what? Half m vx square plus vy square plus vz square is equal to 3 by 2 kBt. Alright? 3 by 2 kBt. So each term will give me what? Half kBt. Then only I will get 3 by 2 kBt, isn't it? Only if each term gives me half kBt, I will get 3 by 2 kBt. So half kBt. Okay. So that's why Vx square is equal to Vy square is equal to Vz square is equal to half kBt. Okay. Hmm. Or, no. See, half m v square is equal to like 3 by 2 kBt. So 2 gets cancelled m. Uh, it will be kBt by m. Sorry, kBt by m. My bad. Should be kBt by, yeah. I did wrote kBt by m. No? kBt by, yeah, kBt by m. Sorry, I'm telling something else. kBt by m. Okay, but Vx into Vy expectation value is 0. All right. So if we put the values, Vx square plus Vy square plus V2 Vx Vy, that will be kBt by m plus kBt by m, that will be 2 kBt by m. Yeah. Yeah, there will be 2 kBT. The answer is 2 kBT then. Right? Next question. Number 5. Consider the CO molecule. Consider the CO molecule as a system of as a system of 2 point particles as a system of 2 point particles, okay, which has both which has both which has both translational and which has both translation and rotational degrees of freedom. Translational and rotational degrees of freedom. Okay. Using classical statistical mechanics, using classical statistical mechanics, okay, the molar the molar specific heat, specific heat, CV of CO gas is given in terms of Boltzmann constant Kb as CO molecule as a system of 2 point particles with both translation and rotational degrees of freedom. Using classical statistical mechanics, the smaller specific heat CV of CO gas is given in terms of Boltzmann constant Kb by. Okay. CO molecule as a system 2 point particles. Both translational is there and rotational is there. Okay. Degrees of freedom. Using classical statistics, the molar specific heat CV is given on terms of Boltzmann constant. So we know what uh, we know average kinetic like this energy is F translational like N F by 2 translate F by 2 kBT, hmm, F by 2 kBT like translational plus rotational plus like vibration plus N F by 2 kBT F by 2, this is your what, rotational kBT, plus N into only F vibrational kBT. Okay, no, there is no half here in terms of vibrational. So for diatomic molecule, the question in the question that is for diatomic diatomic molecule, okay, F translational is equal to 3, F rotational is equal to 2. That is given in the question. So vibrational is not given. So vibrational is a 0, isn't it? So I will just put it here, these values. So this one will be um, how much n is not given. So we'll just put simply 3 by 2 kBT, okay, plus 2 by 2 kBT. Yeah. So the answer will be 3 by 2 kBT plus kBT. That will be what? 5 by 2 kBT. Okay. This should be my answer. Yeah. But oh, sorry. This is your internal energy and average internal energy. What is asked? CV. The smaller specific heat CV. CV is what? du by dt. We know that. If you take the derivative with respect to temperature, so CV will be du by dt. That will be d by dt of 5 by 2 kBT. That is your 5 by 2 kV. Okay, this will be the answer. All right. Yeah. So this question came in TI for 2014. Yeah. See through it again. If you have any doubt, let me know in the comments. Okay, next question. We'll move to the next question, number 6. Question number 6. There will be two containers. Two containers are maintained at the same temperature, the same temperature, and are filled with ideal gases, ideal gases whose molecules have mass m1 and f2 respectively, mass m1 and m2 respectively. Okay. The mean speed of the molecules, mean speed of the molecules, okay, of the second gas is 10 times the RMS speed of the molecules of the first gas. Find the ratio of m1 and m2 to the nearest integer. To the nearest integer. Two containers are maintained at the same temperature and filled with ideal gases whose molecules have mass m1 and m2 respectively. The mean speed of the molecules, the second gas is 10 times the RMS speed of the molecules of the first gas. Find the ratio of m1 by m2 to the nearest integer. Read the question first one or two times, then I will solve it. Okay, so what is given? Mean speed of the molecule of the first gas, sorry, second gas is 10 times the RMS speed of molecule of the first gas. So we need to know what is the mean speed. Mean speed is from how much? 8 kBt by pi m, isn't it? Root over 8 kb. RMS is what? 3 kBt by pi m. It's 3 kBt by m only. No pi. The pi is only will be in mean. Okay, so we'll just put it. So VRMS, V mean 8 kBt by pi m, yeah, m2. M2 is equal to 3 kBt by m1. Taking the square on both sides, 8 kBt by pi m2 is equal to 3 kBT by m1. So kb gone, hmm, T gone. Okay, because it's written in the question, they are maintained at the same temperature. Okay, mass m1 and m2 are only given. So now what is the question? M1 and m2 you have to find. So simple. See, m1, just take to this, m1 by m2 is equal to 3 pi by 8. Okay, that is 3 into 3.14 by 8. Is that, oh, sorry, I missed a 10 here. So it will become 100. Isn't it? There is a 10 here. I missed it. Sorry. 100 into 100. Okay. So that will be, if you calculate, 9.58. So it's around 1.17 into, okay, let's calculate it anyway. 17.7 around or something. No, sorry, 117.7. Calculate the nearest integer, it's na? Yeah. So you have to write 118 is the answer. Okay. M1 by M2 is equal to 1 by, oh sorry, 118. Okay. You see it again and let me know if you have any doubt in this question. Let me know in the comments. Remember this V mean is 8 kBd by pi m, VRMS is 3 kBd by m, root over V average is 2 kBd by m, root over. That's how I have to solve it. Okay, next question. Number 7. Number 7. There is a, this is hydrogen, this is a carbon, this is nitrogen. Okay. This is a hydrogen cyanide molecule. So it follows that, so molar specific heat of hydrogen cyanide gas at constant pressure must be, it's a TIFR 2019. Okay. So if you see, HCN is a linear triatomic molecule, isn't it? Triatomic molecule. Linear triatomic molecule. Okay. So degree of freedom is 3n minus c, isn't it? So 3 into n, that is number of molecules, 3 minus c, that is 2. Alright. This is 9 minus 2, that is 7. So how can we divide 7? A degree of freedom 7, I can divide it. F translational will be 3, F rotational will be 2, and F vibration will be 2. Okay, this is the division. So if we know CV is what? CV is what? F translational by 2 plus F rotational by 2 plus F vibration. There is no divide by 2 in vibrational. Okay, so 3 by 2 plus 2 by 2 plus 2. That is 3 by 2 plus this 1 plus 2, 3. That gives me 9 by 2 R. Okay. So what is asked in the question? Molar specific heat of this at constant pressure. That means pressure with Cp we need to find. Okay. We know Cp minus Cv is equal to R. So Cp is equal to Cb plus R. So here 9 by 2 r plus r. That will give me 11 by 2 r. That is 5.5. Okay. So this is the answer. This is how you solve these questions. Alright. This came in TIFR 2019. So it's not that hard. It's you need practice. More and more practice will really help you. Okay. Okay then. That will be it for this class of thermodynamics. We'll solve more questions in the upcoming videos. Alright. This was from kinetic and theory of gases. This part. Okay. So we'll be solving more. Alright. Thank you very much.